Welcome back after your hopefully enjoyable 2 weeks of Easter holidays, and I do sincerely hope that you took a break, because the next couple of weeks are going to be pretty intense. It looks, for all intents and purposes, that this is going to be the norm right up until the end of this school year, the end of May. Very little chance that we're going to be back to school. Everybody at the primary schools, very little chance that we're going to be back. So this is going to be the new norm. So again, look, I'm appealing to you. Try and keep up with the work that I give you. Try and attempt the questions that I give you to do. We will have a live class once or twice a week, and that's where you bring your difficulties, and we'll go through them then. But apart from that, material that we cover between now and May, we won't be able to cover again when we go back in September. So just keep that in mind. This is one run through this stuff, one run only, and then we get this out of the way. We will have some type of a summer test, whether it be online or whether it be a paper that I send to you and you do at home and whatever, send back to me. That's something we'll work out in the next couple of weeks. But up to then, we've got a couple of chapters to finish. We did finish off roughly halfway through the line chapter. We're going to return to coordinate geometry to line, and we're going to look at a thing called linear relationships with their particular graphs. Now, a linear relationship is exactly what it says. It's a direct relationship, okay? And usually in mathematics or in science, when we get a straight line always tells us that there's a direct relationship between two quantities. Now, what are the two quantities? Well, I suppose generally speaking, the two quantities are always an independent variable and a dependent variable. Okay, now you might say which is which. Well, the easy way to remember it is if you think of the first letter of the word independent, it's I. So therefore, whatever I do is the independent variable. So what I do is the independent variable, and then whatever the response to that action is, that's the dependent variable. So just to take a look at the table I have in relation to the question I'm talking about here. You've got sales and you've got advertising. Now, I advertise. If I'm a business, I advertise. And the response to my advertising is hopefully an increase in sales. So in relation to this table here, it would be easy to say that the advertising is the independent variable, and the sales would be my dependent variable. Okay. Now, why am I talking about independent and dependent? Well, for one very simple reason. When we're drawing a graph, we've got an x-axis and we've got a y-axis. Okay. The x-axis is always the independent variable. So if I was to ask you to draw a graph of this particular set of values here, the relationship between advertising and sales, the first thing you try and figure out is, well, which goes on what axis? And the answer is the independent variable goes on the x-axis. Now, what's the independent variable? Well, the independent variable is the one of these two that I actually do. If I'm a business, I advertise. The response to my advertising is hopefully an increase in sales. So advertising is what we would call my independent variable, my IV, and the sales will be my DV, my dependent variable. Okay, now that's just an example as we go along. So I'll show you in the next slide a way in which we can actually do a question, and it'll make it a little bit clearer, hopefully. Okay, so a lot of real life problems involve what we call a linear relationship, or a direct relationship between two variables, the independent variable and the dependent variable. And as I've said already, an independent variable is what I do. Okay, just keep that in mind. The dependent variable is the response to what I do. So in this case here, if I advertise, the response is an increase in sales. So the advertising would be the independent variable, and the response, which will be an increase in sales, will be the dependent variable. Okay. Now, there's one thing you have to remember in terms of time. Sometimes people get confused with time. What's time? Is time a dependent variable? Is time an independent variable? Well, time is always an independent variable. Time always goes on the x-axis, for the very simple reason that changes in time bring about changes in some other variable. So in other words, if you were to look at a company's sales over a number of months, the months are the independent variable, and then the response to that extension in time is an increase or decrease in sales. It's a trend. Okay, but just keep in mind, the independent variable always goes on the x-axis. If time is involved, time is to be taken always as an independent variable, and that's to go on the x-axis as well. Okay, so if time is involved, we said here, it always goes on the x-axis. Now, let's take an example. A beaker of cold water was heated in the lab. The temperature was recorded at 10-minute intervals as shown. Now, who's the independent variable? Who's the dependent variable? Time is the independent variable, because as I allow time to go on in steps of 10 minutes, there's a response, there's a change in temperature. Okay, and here what we're doing is we're heating up water. So we've got time on the x-axis from 0 to 40, and we have temperature on the y-axis going from -5 up as far as 15. So therefore, if we were going to draw this, we would only need the positive aspect of the x-axis. We would need the positive aspect of the y-axis as well, with a small bit given to the negative aspect of the y-axis. All right, so something similar to this one. Draw a linear graph to represent the data. Now, it's difficult for me to draw a linear graph here on this tablet, so instead what I'm going to do is I've already pre-drawn it by using a set of graph paper and a set of points. So that's what my graph is going to look like. Okay, and again, notice down here we have time, and it's very important that you label your axes. Otherwise, we don't know what we're comparing. So this is time, and this is time in minutes. And this up here is temperature in degrees Celsius. So it's just important that you would label your two axes as you draw them. And notice what I said. We will need all the positive aspect of the x-axis. We need the positive aspect of the y-axis, but we also need a small amount of the negative aspect of the y-axis in order to take into consideration that -5 is one of the temperatures that is recorded. Okay, what could they ask me about this? Well, question B, what is the slope of the graph and what does it represent? And this brings us back to the very beginning. So you have to cast your mind back to pre-2 weeks, pre-the Easter holidays, and try and figure out, okay, how do I get the slope of a line? It depends on the information that's given. Here, the information is given to me in two ways. First of all, it's given to me as a set of points. So I could use y2 minus y1 over x2 minus x1, perfectly fine. But it's also given to me as a graph. So therefore, what I could do here is I could draw my triangle on the line and use rise over run. And just to show you that both of them do give exactly the same answer, let's use both. So slope equals y2 minus y1 over x2 minus x1. And all I've got to do then is take a pair of points. So let's take this point here, and we'll take this point here. So y2 minus y1, that's 10 minus 5, over, now don't forget, if that's y2, then this must be x2, so therefore it's going to be 30 minus 20. 30 minus 20. So that gives me 10 minus 5 is 5. Then we've got 30 minus 20, which is 10. So therefore we get an answer of a half. That's my slope. Let's check and see, does it work with the triangle? So we draw a triangle, as I told you already, a right angle triangle between any 2 points. There's the right angle. And then we've got the rise over the run. And keep in mind that when you're getting the rise and the run, it's one continuous journey along the horizontal and the vertical from one point to the other. So let's start here. We've got a run outwards of what? 20, 25 and 30 of 10 units. And we've got a rise upwards of 5 units. So therefore the rise over the run is going to give me what? 5 over 10, which is exactly the same as what I have here. It's a half. Okay, so therefore you've got two ways in which you can answer that question yourself. Totally up to you. You can decide whatever way you want to do it. Use the triangle on the line if you have a pair of points, or else just use the y2 minus y1 formula over x2 minus x1, and both of them will give you the slope. Okay, part C. Find a formula to represent the linear relationship. Now, what do we need in order to get a formula to represent the linear relationship? How do I translate that into maths? Find a formula to represent the line. Okay, now the formula that represents a line is the equation of a line. So therefore, again, we have umpteen ways we can write down the equation of the line. But here, perhaps because I have a slope and I have a point, the easiest thing might be to use y minus y1 equals m times x minus x1. For the very simple reason that I have an x1, y1, that's any point on the line, and I have the slope from the previous part B. So let's fill those in, and let's take this point here. Okay, so y minus y1, that's y minus 5, is equal to a half times x minus x1, which is 20. Now, clear the half if you wish, multiply both sides by 2. 2y minus 5 is equal to x minus 20. And again, if you want to get that line into the y equals mx plus c formula, what would you have? You'd have 2y is equal to x minus 20 plus 5, which will give me 2y is equal to x minus 15. So that's it. All right, that's your y equals mx plus c. And if you want to divide across by 2, y equals a half x, there's your slope, minus 7.5. And again, that's totally up to you. You can leave it this way if you wish, or you can bring it all the way down to y equals mx plus c. That's up to you. Okay, part D. Just let me remove some of this writing here. From your graph, estimate the time taken to rise from 0 to 15. So just let me get rid of some of this here. Apologies for that, but you know how that's done. So I just need to clear this so we can see what we're doing. Okay, so use your graph to estimate the time taken to rise from 0 to 15. Now, from 0 to 15. So 0 degrees is here, 15 degrees is here. Okay, so if I'm going to run from 0 to 15, that's from here. There's 0 on this axis, so it's from there all the way up to here. What are the corresponding points on the x-axis? This one here and this one here. Now, if I take the 0 to 15, what I'm looking for is how many seconds does it take me to go from that point to this point here? And the answer is whatever the run is on the x-axis. So from 10 up as far as 40, which is nothing more than 30 seconds. Okay, so again, you can read that from your graph. And part E, what does the Y-intercept represent? Now, this is the way in which we have to try and extrapolate data. So when we're given a graph like this, we have to remember this mathematical graph is the representation of a real-life situation. Here, it's the heating of water as blocks of 10 minutes pass by. We're heating water in the lab over a space of 40 minutes. Okay, what does the Y-intercept represent? Well, let's just follow this line back until it hits the y-axis, and it hits the y-axis here. Okay, what does that represent? That represents -5 degrees at a time of 0. So this is -5 degrees Celsius at t equals 0. How do I make sense of that? What's t equals 0? In every single experiment we do, t equals 0 is the starting temperature. T equals 0 is the beginning, okay? And you need to remember that going forward. So anytime we ever meet t equals 0, that's the very beginning of our experiment. So what does the y-intercept represent? The y-intercept represents the temperature of the water at the very beginning of our heating exercise. So -5 degrees at t equals 0 tells me that when I was starting this experiment, the temperature of the water was -5 degrees Celsius. And lastly then, what would the temperature of the water be at 29 minutes? So 29 minutes is where, again, this is information that comes from the graph. This is called extrapolation. You're taking information from the graph that has been drawn on a limited set of points, and we're trying to get more data from this than the table would actually give. So what would the temperature of the water be at 29 minutes? Well, first of all, because it's 29 minutes, we go to the x-axis. We find out where 29 minutes is. There's 25, 26, 27, 28, there's 29. Okay, now, what would the temperature be? And I'm just going to clear everything from here. I'm just going to erase all. And I'm going to do this again. So from 10, we want to go to 29 minutes. There's 25, 26, 27, 28, there's 29. Okay, now all I'm going to do here is bring that line up until it hits the graph. And when it hits the graph, we then take an immediate right turn, which will bring me to here. Excuse my straight lines. You can do much better than this, but you'll be using a ruler. And we get an answer of exactly 9.5, roughly about 9 degrees. This is on the degrees. So we're going from time up to the graph and over to the degrees Celsius. So the answer there is roughly 9 degrees C. So after 29 minutes, we're hoping that we'll be at a temperature of 9 degrees because that's what the graph tells us. That's what we extrapolate from the information that's given. So they're not that difficult. The biggest problem is, where do I put the values on the x-axis and what values do I put on the right axis? Who's my independent variable and who's my dependent variable? Okay, so I'm going to leave you now with these questions. Page 271, 286, 287, 288. These are real-life situation questions. They're questions that are going to get you to draw a graph. They're questions that are going to ask you about the line that you draw. And if they do, by the way, if these questions do produce a line, then they are producing what is called a direct relationship. And just keep that in mind. A straight line is always a direct relationship. Okay? Just keep that in mind. It's extremely important. So straight line is a direct relationship. They're going to ask you about the relationship. They're going to ask you about probably the slope of the line. They're going to ask you about the equation of the line. And then they're going to extrapolate extra information that only the graph can give that is not present in the original data that was used to draw the line. So short lesson today. That's it. I want you to work on those questions. 271, 286, 287, 288. And then we'll come back the next day with we're going to move on to the the cutting up of a line segment in a different ratio, or the breaking of a line segment into a given ratio, but we'll do that when we come back after these questions.